So, we are going to solve a problem on transient conduction. The problem that we are going to solve, it consists of a thin cylindrical wire, and the cylindrical wire has some resistance, electrical resistance. It is submerged in an oil bath whose temperature is lower than that of the wire, and while the current flows through the wire. The convection coefficient for this specific case is provided. So, a wire whose electrical resistance is provided, the amount of current that flows through it is given. It is submerged in a liquid bath, oil bath, whose convection coefficient, the convection coefficient for this case is known. What we have to find out is what is the steady state temperature of this electrical wire, and how long does it take for the wire to reach within 1 degree centigrade of this steady state value. So, I have written down the problem in this way. What I have then is we have a long wire of diameter 1 millimeter. The electrical resistance per unit length of this wire is 0.01 ohm per meter. It's submerged in an oil bath whose temperature is 25 degree centigrade, and the entire process is governed by a convective heat transfer coefficient of 500 watt per meter square Kelvin, and the current which flows through this wire is 100 ampere. What you have to find is what is the steady state temperature of the wire and what time is needed in order for the wire to reach a temperature which is going to be within 1 degree centigrade of the steady state value which you have calculated in the first part. The density of the solid material of the wire, material of construction of the wire, is 8000 watt per meter cube, 8000 kg per meter cube. The heat capacity is 500 joule kg Kelvin, and the thermal conductivity of the solid material is 20 watt per meter per Kelvin. So, these are the two things which we have to find out. But before we start this problem, one first have to find out what is going to be the Biot number in this specific case, such that we would be able to determine whether or not lumped capacitance model is valid. So, Biot number is, this is a cylindrical system. So, ideally this should be R 0 by 2, which is the characteristic length, but as I mentioned before, in order to be on the conservative side for calculating the Biot number and to decide about the applicability of lumped capacitance model, generally the characteristic length is taken to be the length scale across which you get the maximum change in temperature. So, obviously, when a thin wire is placed in an oil bath, the maximum temperature is going to be at the center line of the wire, and as we go towards the periphery, the temperature will decrease, and right at the periphery of the solid cylindrical wire, the temperature is going to be the least before it starts convection to the cold oil bath. So, the maximum difference in temperature, maximum drop in temperature is taking place over a length scale which should be equal to the radius of the cylindrical wire. So, therefore, the characteristic length for this specific case, in order to remain conservative, is taken to be equal to R 0, which is the radius of the cylindrical wire, and Biot number is calculated based on this value of R 0 and not R 0 by 2, which was predicted by the formula for the characteristic length. So, Biot number is H R 0 by K, and when you plug the numbers to be equal to 500 into 5 millimeters, so 5 into 10 to the power minus 4 by K, which has been given as 20, is 0.012 and it's less than 0.1, so which shows that LC, the lumped capacitance model, is valid. Now, if the lumped capacitance model is valid, then T is not going to be a function of R and T is going to be a function only of time. That is what essentially lumped capacitance model is. Now, when we think about the steady state temperature, the steady state at the steady state, whatever heat that is produced, heat generated must be equal to heat that goes out, heat out by convection. So, heat out by convection would simply be equals pi d L H, temperature of this solid, which is a function of time but not of space, T times T infinity, and the amount of heat that is produced is I square R, where R is the resistance of the wear. So, I bring this L to this side and make it as R by L. So, when I make it R by L, this is nothing but the resistance per unit length of the wear, and this is how I denote it. So, resistance per unit length of the wear. So, initially I started with I square R equals pi d L, the surface area times H T minus T infinity, brought the L to this side and make R by L equal to R E prime, which is a resistance per unit length of the wear. So, I have the relation as I square R E prime to be equals pi d times T minus T infinity. When you plug in the numbers, you simply get T equals T infinity plus I square R E prime by pi d H, and you put the value of T infinity, put the value of A to be 100 ampere square, R E prime is 0.01 ohm per meter, and pi, the diameter, is 0.001, and the value of the conductive heat transfer coefficient is H, which would give the temperature to be the steady state temperature to be equal to 88.7. So, the steady state temperature of the wear by a simple heat balance would be equals 88.7 degree centigrade. This is the part 1 of the problem which we are dealing with. So, in the next part we have to find out how much time is needed for the wear to reach within 1 degree centigrade of the steady state value, or in other words, what is the time that is needed in order for the wear to reach a temperature of 87.7 degrees centigrade. In order to do that, we first have to realize that what is going to be my governing equation for the transient. So, this here we are talking about the transient case, and in the transient case the fundamental equation in minus out plus generation is equal to stored. All these are rate. So, rates of energy in minus rates of energy out plus generation rate is equal to the rate at which energy is stored in the system. Of course, nothing comes into the solid, but there is a convection in which heat is lost to the surrounding, but at the same time, since we have a current which is flowing through the wear, some amount of heat is going to be generated, as a result of which the energy stored would be different. If you remember the development that we have done so far, out was equal to the amount of energy, rate of energy stored. there was no generation term previously in our expression. But each problem you have to be careful before using any formula, just to make sure that the problem at hand exactly conforms to the assumptions or descriptions of the problem, textbook problem, which based on which some relation or a correlation was developed. So, I cannot directly write the expression which was obtained in the last class for transient conduction, because in that development there was nothing called a heat generation term. But here I have a distinct heat generation term while it is undergoing transient conduction. So, it is better to start from the fundamental rate equation for heat transfer and see which are the terms that are not going to be present. And if it conforms to the textbook problem, only then textbook situation, only then you will be allowed, you can use the expression derived under such condition. But here we clearly see that we have a heat generation term that makes this specific problem distinct from what we have analyzed previously. Therefore, we need to use, you need to start from the fundamentals, from the basics, and derive an expression for the temperature distribution, for the time variation of temperature on our own, and use that expression to obtain what would be the time needed for the wire to reach a temperature within 1 centigrade of the final, that is steady state temperature. So, we start with this equation. The heat that goes out would be H times pi d temperature, which is a function of time, minus T infinity. Look here that I did not include an L term, the length scale term, the characteristic length in here. So, all what I am doing, this heat out term is on a per unit length basis. So, the heat out is on a per unit length basis. Therefore, it would be possible for me to write the generation, which is simply Joule heating times R e prime. I can use R e prime, which is resistance per unit or resistance per unit length, because I brought this L down at the denominator of the resistance and make it resistance per unit length, divided by I square R e. And on the stored side, I have rho c, the density, the heat capacity, and the volume, pi d square by 4 into L. However, everything is expressed in per unit length basis. So, L will not appear in here. So, rho times pi d square by 4 times L would give me the mass times C. So, mCp and the change in temperature with time. So, that is the time rate of change of energy stored in the solid on a per unit length basis. So, this is heat out, convective heat out of the solid on a per unit length basis, where the temperature is the instantaneous temperature, and since the value of Biot number is less than 0.1, this is only a function of temperature, only a function of time, and not of any space coordinates. T infinity is the fixed temperature of the liquid. I square R e is the heat generation per unit length, and this is the rate of energy stored per unit length in the solid. So, a slight rearrangement would give you as I square R e prime rho c pi d square by 4 minus 4 h by rho c d times T minus T infinity. This is the governing equation which I need to integrate in order to solve for the time needed for the temperature to reach a specific value. So, I define theta is equals T minus T infinity, and all these big expressions are put into in the form of new constants as a and b, where they are defined nothing but what we have here are e prime by rho c pi d square by 4, and then this expression would be simply be equals d theta by dt plus a theta is equal to b. So, this is the compact form of the governing equation, where this is b and this is a and t minus t infinity is theta. So, it is d theta dt plus a theta equals b. So, it can be solved, this ordinary differential equation can be solved in using an integrating factor, which is a e to the power a t. So, you can integrate it once to obtain the final form as theta e to the power a t is equal to b by a e to the power a t plus c. So, therefore, theta, which is t minus t infinity, is equals to b by a plus c e to the power minus a t. This c is the constant of integration, which needs to be evaluated through the use of boundary conditions. But once again, what we have here is then t minus t infinity minus b by a is equal to c e to the power minus a t. The boundary condition that can be used is at t equals 0, the temperature is the initial temperature of the solid wire. So, therefore, T I minus T infinity minus b by a is equal to c, and this is at t equals 0. So, this is my equation 2 and this is my equation 3. So, this is the boundary condition that has been used in order to evaluate c. So, what I do is I divide equation 2 by equation 3, and what we get is t minus t infinity minus b by a, b and a are both constants, by t I minus t infinity minus b by a is exponential. If I put back the value of a in here, minus 4 h by rho c d times t, and from the definition of b and a, we know that b by a is, you can figure out that b by a is I square R e by pi d h. So, your temperature is given as 1 centigrade within 1 centigrade of the steady state temperature. The steady state temperature was 88.7. So, a final temperature of 1 degree within that temperature, steady state temperature, would be 88.7. The T infinity is 25. The B by A, when you plug in the numbers in here, you would see that the number is 63.7. The H is 500. I am not using the units. You can put the correct units corresponding to each of these terms. The rho is 8000 kg per meter cube. The C is 500, and the diameter is provided as 0.001 meter. So, when you plug these numbers, plug all these numbers in this, you would find out the unknown time is to be equal to 8.3 second. So, this example tells you how to solve a transient conduction problem using understanding the physics of the problem, which may have a different form than that present in your textbook development of transient conduction, or any development for that matter. So, you should always be on the lookout for cases which differ from the standard cases, and if you understand the physics of the process, you would be able to incorporate those changes in your development process so as to obtain an expression which would be valid for the specific case that you are handling. So, this concludes our part of the transient conduction process. There are many more things in transient conduction that I did not touch upon in this course, but I think you will have a fair idea of that when you go through any textbook on the transient on heat transfer in the chapter transient conduction. This specific part I have used from the book to use is Incropera, the book of heat transfer by Incropera and DeWitt. The entire part, the transient conduction part, was you should be able to find in the book of Incropera and DeWitt. Now, next we move into a problem which is slightly more involved, in which will continue in the next class, since we probably do not have enough time today, is the case of force convection. So, what I would do is I will simply introduce the problem in this and identify the different mechanisms by which energy gets transported in here. So, this is a pipe through which a fluid at some given temperature T0 is coming into the pipe, and it's a cylindrical pipe where a constant heat is being applied through the sidewalls of the pipe. Okay, so, this is the constant heat which is being applied to the pipe, and let us call this constant heat flux. The constant heat flux that is added to the pipe is Q1, and as the fluid is moving, it is going to receive some amount of energy from in the art direction by conduction, and we also realize that the temperature of the fluid will increase as a result of convection as well. So, we have a system in which both conduction and convection are present. There is a constant heat flux which is being supplied through the sidewalls as the fluid is moving. So, as the fluid is moving, it is going to gain more and more energy, which would be manifested by an increase in temperature of the fluid. But unlike the cases that we have dealt with before, the temperature profile of the fluid is not only going to be a function of axial position, which let us call it as Z, it is also going to be a function of R, where the fluid particles are located with respect to the sidewalls. So, this is a case in which both conduction and convection are present. It is going to be the temperature profile will vary with the axial position, and at a fixed axial position the temperature will also vary with the radius with the radial position. So, looking back at the figure again, the fluid is moving, it is a constant heat flux which is being added, and you have both conduction plus convection which are present in this in the system. Now, whenever you have convection present in the system, you are dealing with a velocity of the fluid. So, if you are talking about the velocity of the fluid, the convection is induced by the velocity of the fluid, and we understand that when a fluid flows in a pipe upon the action of gravity as well as an imposed pressure gradient, in laminar flow the velocity profile that you would expect is going to be parabolic in nature, which we have done in our treatment of the fluid mechanics part, momentum transfer, where we saw that the profile is going to be laminar, it is going to be parabolic, and the velocity is expressed with the following formula, that Vz is equal to Vz max times 1 minus r by r whole square. So, this is the parabolic distribution of velocity, and the Vz max, the maximum velocity, which obviously takes place at the center line, is expressed in terms of the pressure, and if you remember correctly, this P0 contains the effect of both the imposed pressure and gravity. So, P0 minus PL is the total effect of gravity force, the body force and surface force. So, P0, if I would advise you to go back to at the beginning of this course and see the derivation of the Hagen-Poiseuille equation, or flow through a pipe in presence of a pressure gradient and when the body force effect of the body force is important. So, if we do that, we would see that P0 contains both the pressure, imposed pressure, as well as the effect of gravity. So, it is important, it is a prerequisite in order to solve the heat transfer problem in which there is flow and the walls of the pipe are receiving a constant heat flux. One need, since it involves convection, one needs to know what is the velocity distribution. So, to solve a heat transfer problem, it is imperative, there is a prerequisite that we solve the fluid mechanics part of the problem first in order to obtain the velocity profile, and this velocity profile can then subsequently be used in order to find out what is the convection, what is going to be the convective flow of heat in such a system. So, solution of fluid mechanics is prerequisite for the solution of heat transfer, and as I mentioned previously, there is a coupling between fluid momentum transfer and heat transfer, and the coupling will always be one directional, that is fluid then heat and not the other way around, provided the physical properties remain constant. If the physical properties rho, Cp, mu, etc. do not remain constant, then there is going to be a two-way coupling and a simultaneous solution of heat and momentum transfer has to be done to arrive at the expression for velocity as well as to find the expression of temperature. So, looking back at this figure once again, since it is a case of conduction and convection and the temperature varies with Z. So, this is my R direction and this is the Z direction. So, here we see that the temperature varies with R and the temperature varies with Z. So, if I have to assume a shell for our balance, the shell will be something like this. The shell is going to have a length equals delta Z, since the temperature varies with Z, and since the temperature varies with R, the other dimension of the shell, imaginary shell, across which we are going to make a heat balance must be equal to delta R. So, see the problem that we are facing right now. So far we were visualizing only one smaller dimension and making a heat balance, but now since the temperature is a function both of R and Z, the shell that we have to think of and the shell across which all heat entry are to be balanced has two smaller dimensions, one is delta Z, the other is delta R. And through the top surface, through the annular top surface, which has an area of equal to twice pi r delta R, you are going to have convective flow due to the motion of the fluid as well as conductive flow since the temperature varies with the axial position. So, T is a function of Z. So, variation in T at different values of Z will initiate a conductive heat flow in the Z direction, which would enter into the control volume through the annular area twice pi r delta R, and I have a convective flow. On the side walls of my imaginary shell, I am going to have conductive flow of heat conductive flow of heat, but since the flow is one dimensional, the flow is only in the z direction, there is not going to be any convective flow through the surface that I call as delta z. So, through one boundary of the control volume, I have both conduction and convection. Through the other boundary of the control volume, I have only conduction. So, in order to write our balance equation, we need to express conduction in the z direction, convection in the z direction, conduction in the r direction. So, all those will have to be taken into account to derive a governing equation of this, and the treatment of this will underscore the utility of having a generalized equation, which, like the Navier-Stokes equation that we have discussed before, will make it possible not to use this shell heat balance for complicated geometries, but have a general equation in which all the terms which are not relevant can be cancelled to obtain the final form of the energy equation, the final form of the heat transfer equation. So, we would go to some extent in solving this problem using shell balance, but from next class onwards, from the class after that, we will switch to the formulation of a generalized energy equation, and from that point onwards, all problems of heat transfer, be it convection or conduction, will be handled by looking at the right component of the energy equation, cancel the terms and arrive at the final governing equation.